Good day, everybody, depending where you are. Good morning or good evening. And so I'm very pleased today we have Professor Marco Campi, who is an Italian colleague of mine, who will be presenting a tutorial session on scenario optimization. And so this will be our last event for the spring season of stochastic programming seminars. And we intend or plan to resume this series on next September, very likely on September 13, but we will be posting, the information. So let me come to Marco very, very briefly. Marco is a professor at the University of Brescia, which is a very nice university in northern east of Italy with a long tradition in industrial engineering and industrial optimization, has a strong, historically is a stronghold of industry development in Italy. And then his background is in engineering. He's a fellow of the Institute of Electrical and Electronics Engineering, and also of the Institute of, actually the International Federation of Automatic Control. So he is a control theorist and applied mathematician, with very skillful in probability theory and popular in our community for his contribution on scenario optimization, particularly. And in general, since I know him, working together with Simone Garatti, who is professor, in Polytechnic of Milan, and Aldo Carré, who was actually a PhD student in my university in Italy. So what can I say? His contributions are primarily in the area of control problems, and then stochastic control problems, and the design of optimal control techniques under very, very general assumptions on the probability distributions, and in particular with a focus, which is the one that he will be taking during this tutorial, on data-driven methodologies. So thank you, Marco, welcome, and please, you can deliver your tutorial.
Right, so thanks so much, Giorgio. Thank you for the invitation to the organizers, to Professor Marco Campi and Professor Giorgio Consigli in particular. It's a great pleasure to be with you here today. And I feel flattered to get this presentation in this very nice series. So the title, I think that you see from my screen, I'd like just to take a moment to highlight a couple of keywords in this title. One is data-driven. As Giorgio mentioned before, I mean, I'm really doing a data-driven optimization, and all you are going to see in this presentation really refers to optimization based on data. The second keyword is a certified reliability, because our goal is not just to come up with a method, but we also like to certify the method. So to come up with certificates of reliability for the method. Let me say that this talk is in two parts. In the first part, I will put forward my vision when it comes to data-driven optimization. And I will also tell you of some of the desiderata that I think one should have when doing data-driven optimization. And in the second part, I will instead focus on scenario optimization, which is a very general methodology, which may provide some answers to the desiderata that I will talk about earlier. Okay, so I would like to start with the part number one, and I would like to address first this quandary, which I believe is very central, very fundamental for data-driven optimization, indirect or direct. So indirect, of course, means that we use the data to come up with a description of the probability distribution of uncertainty. And then based on that, we optimize. Direct instead refers to a direct use of the data to optimize. So that's kind of repeating the same concept. Stochastic programming deals with the optimization problems, wherein uncertainty is described by means of probability distributions. But should we use the data to obtain such a description? Or rather, should we aim at directly optimizing? I believe that these questions are especially important in today's world as we confront increasingly complex problems. So in order to address this first issue, I thought that the best was to use a couple of examples. So this is my first example, portfolio optimization. And in fact, this example brings me back to a few years ago. That time I was visiting Imperial College in London, and I had a chat with Mark Davis. Just to those who haven't had the fortune to meet Mark, he was a super scientist in quantitative methods for economics, but also in a stochastic control. Anyhow, so we were chatting about how portfolio optimization could be done. So who's giving us the description for uncertainty? And I remember Mark telling me, do you trust Black and Scholl's theory? I said, yes. And then he said, then you must accept that stock prices follow a log normal distribution. Therefore, you use the data, and you estimate the parameters of this distribution. So all well and good, but let me describe a bit more closely. So say that we got the assets. PK is the percentage of capital invested on asset K. We group together the PKs in the optimization variable theta. And then this is the function we would like to optimize, J, is a sum PK RK. RK is called rate of return, is a closing price minus opening price divided by opening price, and it is uncertain because it depends on the evolution of the market. So we group together the RKs in delta, and now we have a function J theta delta. Theta is the optimization variable, and delta is the uncertainty parameter. PK-RK is how much money we make by investing percentage PK on asset K of 1 unit of money. When we sum, we get the return of the portfolio. The point is, if we have the distribution for prices, we can infer the distribution for the rates of return, and then we get the full picture. Hence, we can use whatever risk measure. We can use a value at risk, a conditional value at risk, and we optimize. However, let's look a bit more closely to the number of parameters. Say that D is 100, and 100 assets is certainly not extreme at all. At times we use 200s, at times 300s, at times 500s in a portfolio. With 100, we get 5,150 parameters to be estimated. So, for example, suppose that this is a daily investment. In order just to equalize the number of parameters with the number of data points, considering that, in the market, normally in a year there are 252 trading days, you have to look at the a time window of 20 years. And really, it is hardly believable that the distribution will remain constant over such a long time window. So even a simple problem like this one is already challenging. And this problem is finite dimensional because we do have finitely many parameters to estimate. This is my second example. This is a defibrillation. It's an application I've been working on for 10 years or so, in the belief that it has an incredible social impact. So the story here goes that there is a patient down on ground it's called ventricular fibrillation. And in that condition, there is still a remaining electrical activity in the heart, but it is disorganized. So much so that the spontaneous circulation is no longer present. So in that condition, a person dies in 7, 8, 9 minutes, and in half the time, the brain gets completely destroyed because of lack of oxygen. So all guidelines prescribe that if a defibrillator is available, one should immediately place the electrodes of the defibrillator on the patient's chest and give an electrical shock, in the hope that this restores an organized electrical activity and therefore the spontaneous circulation. Point is that this happens at the first shock in only 20% of the cases. And should you know in advance that the shock will not be effective, you should not give the shock, because you lose time, and also there is medical evidence that an effective shock can further damage the cardiac muscle. There are alternatives. So it is recognized that a properly given cardiac massage before shocking really boosts the chance that the shock will be effective. The shock that you give after the cardiac massage. So there is a big challenge in this field, as given by the goal written there, predict whether the defibrillator shock will be effective. I should tell you that any modern defibrillator can do two things. One is giving electrical shock, but also before doing so, all modern defibrillators do another thing. They collect a short ECG, electrocardiographic tracing of the patient. And the challenge is to use this information of the remaining electrical activity in a classifier so as to have the classifier giving you green light, which means yes, shock now because the shock will be effective, or red light, do not shock, the shock will be ineffective. And the European guidelines are openly endorsing this challenge. So it is clearly written that when someone will be able to provide such a classifier, having good enough, and there are precise numbers for that, good enough sensitivity and specificity, then this classifier will be embedded in all defibrillators. So the challenge is to construct a classifier here. But now let me come to tell you what uncertainty is in this application. So a typical data point takes this form. So it's a pair where the input is the ECG tracing and the output is either 0 or 1, ineffective or effective shock. I have data given me by the hospital of Brescia in this form. So the point is, I can very well accept that the uncertainty parameter delta can be described by a probability distribution. But coming up with actually a description of that probability distribution is a completely different matter. And it is a frightening task. If you think of that, the domain for delta is already an infinite dimensional domain because the input is a wave form. And as such, it is an infinite dimensional object. So basically, we are talking here of constructing a probability distribution over a domain which is infinite dimensional times 0, 1. What is normally done in this field is the following. People move down from the ECG to extracting finitely many features. And these are the 9 that are used in this application. Oh, by the way, there is a color code. The 5 in blue are time domain features and in green frequency domain features, but that's unimportant. And often one goes down to fewer features like 4, 3, 2. But let's go to the extreme, just 2 features, 1 and 2. So in this setup, if we want to reconstruct the distribution, we are after reconstructing this distribution, which comes in 2 parts, because red is at the level 1, which means effective shock. 0 is at the level 0, an effective shock. And this is itself an infinite dimensional problem, because we don't have a handle like in the portfolio case where we say log normal. So this distribution doesn't have a predefined shape. So this is a very difficult task again, let alone when you scale up from 2 features to 3, 4. Also, I would like to make a remark regarding what the final goal will be. To explain this, let me shift the red down to the level of blue. And what we are after in this application is this. So this is called the Bayesian classifier. The Bayesian classifier is a 10 in 1, where red outdoes blue, and the 0 where blue outdoes red, simply because this is the classifier that minimizes the probability of misclassification. So this is what we are after. And I believe that you see very clearly that this object is way simpler than the distributions themselves. So if you try first to reconstruct the distribution, to then come up with an estimate of this classifier, basically you are solving a more complex problem to find a resolution of a simpler problem. I would also like to spend a couple of minutes on the distributional robust approach, which is an approach I love. And probably you've seen that there is a lot of activity around about this distributional robust approach. So I would like to convey to you my own take on this. So the story here is that having recognized that using the data to come up with one single distribution is too much, because very often there isn't enough information. Then the goal has been shifted towards constructing a set of distributions, which makes a lot of sense. And the construction, I mean, there is a beautiful mathematics. The construction is such that one can attach a tag saying the true distribution will be within the set with the given probability. So you can choose 98, 95, 99, whatever. And then the design is made robustly with respect to these distributions. So a typical example is the use of a Wasserstein ball to achieve this. I have to say that I really love this approach. There is so much wisdom. So I really have a very positive take on this approach, but I feel that I also have to highlight an aspect that needs to be addressed to make this approach really viable for real applications. And it is, when we construct the region for the distributions, we should really have two goals. One is to construct a region that contains with a high given probability the true distribution. But there is another goal, and it is that we should take an eye on the final goal. So in other words, if I have to decide whether to include in my region this distribution or that distribution to have the given probability, I should look at the one giving not a large impact on the final design. And this is very difficult, very difficult. So it's very difficult to construct these regions looking at the final goal. So I know there is a research being done in this direction, and I very much welcome this research, but this is very difficult. So my only concern about this approach is that it can be conservative, because you construct the region, then you want to find a robust solution with respect to the distributions, let's say in the Wasserstein ball, and this boils down to something that normally is conservative. So let me summarize my points on this first part. For simple problems, the indirect path works well. However, as the complexity of the problem increases, the indirect path falls short. Therefore, in real problems, it may be convenient to aim for a direct path from data to decisions. I have a second point in this first part, second and last point, certified data-driven optimization. So I believe that we, when I say we, I mean the community of people doing stochastic optimization, okay? I believe that we should aim to develop a science for data-driven optimization in the presence of uncertainty. So it is not enough to come up with methods, algorithms. I believe that we should aim at developing a science. Science is something that is supported by a solid mathematical background. So the idea here is that we should provide guarantees, certificates of quality. Now, when I tell people this thing, very often I get back the observation then we need to use priors, which makes a lot of sense. So let me explain why we should need priors for that. So I have a very simple conceptual example for you. So that we have just two data points. These are two data points. And next, I'm giving the x value of 1/3 point. So this is the blue dot. And I'm asked, where is the next point? And say that this is my construction. I connect the first 2 points and I lift my blue to the level of the interconnector line. And then I say, this is my guess. And I want also to give guarantees about my construction. And immediately someone will say, oh, come on, but you're using a prior. How do you know that? I mean, you are doing interpolation. Probably you are assuming that, underneath there is a probability distribution that is concentrated on a straight line. And as a matter of fact, when telling you this story, it sounds so reasonable to me. My question is, should we aim higher? And I tell you what I have in mind. So I will like that. At the time I make a design, I use data and prior information. Prior domain information is something that I may know, but I may not completely sure about. I give you an example. I want to do portfolio optimization, and I have the feeling that the automotive sector is doing better than other sectors like banking or medical sector. So I place more assets coming from automotive, and then I optimize. And at the end of this procedure, I can see the result of my optimization. However, when it comes to guarantees, I would like that my guarantees maintain intact their validity, whether or not the prior I have used is correct or fully correct. Is this at all possible? Okay. So let me come now to the second part, the scenario approach, an eminently direct approach. In fact, let me say you a word before I start. When preparing this talk, I was in two minds as to whether I had to start from the most general setup, which is very abstract, or rather, if I had to start with specific setups. In the end, for the sake of concreteness, I decided to use the second approach. That's why I will start from robust optimization. Okay, so the approach here is the following. You have a cost and you would like to minimize subject to constraints. Delta I is an observation. This is a data point. In this approach, we call delta I a scenario. But you can use observation, data point. These are synonyms. And I have n of them. You optimize, and then you are interested in the risk. What's the risk? Is the probability with which, for one next as yet unseen delta, the solution to this problem will be in violation of its constraint. So it is the probability of violation of the constraint. And then, of course, you can ask, but what do you have in mind? So what's your prototype example for this? Well, let me just tell you that this is a very general setup. So this can be applied to machine learning problems. And in that case, the risk becomes the probability of misclassification. You can apply it to a control problem. In that context, this becomes the probability of not satisfying the control specs. However, since I want to be very concrete, I will give you just an example of the setup. So I will take a short detour, and then I'll come back to this slide. So my example is, say that you want to minimize J theta delta. Theta is optimization variable, delta is uncertainty. You can think of portfolio optimization if you want. So I have n observations, a record of n observations. I can plug them into my J function. And now I have, this is the first function, corresponding to delta 1, delta 2, delta 3. I have n of them. This is what I call a empirical bundle of cost functions. Then say that I want to do min-max, which means I first take max with respect to the delta I. So for any theta, I go up till the largest value. So this max gives the top function, the one in gray. And then I minimize. Doing this, I find theta star and J star. All this is visible because it's only data dependent. And of course, I mean, if it were you, what would you do first? I would look at this value, whether I like it or not. So say that this value is a 3.72, and you say, okay, this value is good enough, good enough. So I'm going to use this design, theta star. Of course, in doing this, you can deceive yourself, because this J star is a value that you have obtained by optimizing over the scenarios. So you have been specifically looking for this point. So this can be deceivingly small. But let me continue. I first rewrite my min-max in this form. I introduce the variable x, which is theta j. I minimize with respect to xj, so I minimize in this direction, under the constraints that j is above the functions. So this is called the epigraphic, you all know it's called the epigraphic reformulation. And of course, this is equivalent to this. And what is the risk for this example? That's the risk. The risk is to see next one delta such that the constraints is not satisfied. So the other way around holds true, which means that the incurred cost is bigger than J star. So the incurred cost is this value. You're going to see a function that ends up in the red region. So this corresponds to a disappointment. So for this case, the risk is the probability of having a disappointment when you say J star is good for me. So I hope to find something having J star value or better. So let me go back now to this slide. This is our program, and note that this program is direct. So this is a program where I use my data points directly. There is no attempt of reconstructing the underlying distribution. The risk cannot be directly computed. And this is so because P in applications is not known to us. Should we know P, the whole problem would disappear, because we would have no need to use data. We use data because we don't have the full picture. So depending on the applications, I can have some clue about P, but P is not known. So I cannot compute the risk according to its definition. And the question now is, can we certify the risk? And I would like to tell you a beautiful story, the story of a beautiful marriage between two concepts, risk and complexity. So I believe that risk, by now you know what it means, so I concentrate on complexity. I will explain what complexity is through examples. So that's the first example, the one that we saw before, that is minimization of J theta delta. Notice that if the scenario corresponding to the top right function had not been seen, then the solution would have been a different one. The solution drops by removing it. Same on the left. Therefore, I say the complexity is true. If only 2 delta I are maintained, the solution doesn't change. So complexity is how many we need to maintain to reconstruct the solution. Very importantly, complexity only depends on the data set, is measurable, does not depend on the underlying distribution. a statistician would say that complexity is a statistic of the data set, is something that we know. I'll give you another example of complexity. So in this case, you see 500 points drawn from a probability distribution. And then I construct the convex hull of the points. Can be because you want to predict the next point to be in the convex hull, but it doesn't matter. Now, in this case, you have 7 points at the boundary. So let me explain the underlying optimization program. So you feed with your data points an optimization program, which is this one. So you want to minimize the volume of your set, and you pick the set from convex sets. The convex hull is a convex set, is the smallest convex set, subject to all the points inside. So this is exactly within our robust optimization program. By the way, I take this opportunity to make a remark. Before I wrote min x cx, and I didn't tell you anything about this x, where it lives. The reason is that in this theory, there is no assumption at all on x. So, for example, it is not required that x belongs to some, finite dimensional vector space. Certainly, the set of convex set is not a finite dimensional vector space. There is no assumption whatsoever. So this theory can be applied to everything, to calculus of variation, so with no limitations on the domain for optimization. Then what you do is you start eliminating one after the other all the observations until you are left with the 7 points at the boundary, and the observation again is, if only the 7 points are maintained, opt gives the same solution. So the complexity in this case is 7. So now you know what the complexity is. The complexity is, there is a notion of compression. You compress the original set into a subset that returns the same solution. Next step is, I believe that somehow intuitively, you can think that low complexity implies low risk. And I'm going to enter this idea in the next slide by giving you an example, and then I provide you with a full theorem. So this is an example that I run together with Simone. Well, by now it's already a few years ago, I would say. I'll tell you what the problem was. We manufactured a probability distribution in 400 dimensions, and we drew 1,000 points. Then we consider the negative orthant. So this is the origin, negative axis, negative axis, negative axis, the negative orthant in 400 directions, in the 400 dimensions. Then we optimized, and the optimization meant we moved the orthant in the negative directions, all the directions, but we wanted to leave the points inside. So in spirit, it's the same as the convex hull. The points must stay inside. In this problem, complexity is the number of points at the boundary, preventing you from further improving. If you look at my fingers, you can see that in 3 dimensions, you may have 3 points at the boundary, but can be 2, can be even 1. If there is just 1 point at the vertex, this is enough, which means that the complexity is a random variable that depends on the sample. So this picture displays the bivariate distribution of complexity and risk for this problem. Oh, by the way, in a real application, you will never be able to obtain this picture. So in this example, we are God. because what we manufacture the distribution, so we were aware of everything. What stands out, I believe, is that there is a lot of correlation between complexity and risk. Complexity is a statistic of the data points. So this suggests in this application that we can wait until the solution is found, compute its complexity, say that the complexity is 250, then you know you are here, and then you estimate quite informatively the risk. When you bump into an example like this one, of course, you start asking fundamental questions like, is this specific to this problem, or is it more general? The answer is, in an IID setup, so you have a distribution and data are independent of each other. In an IID setup, this result holds true universally. Always. Doesn't matter the domain for optimization, doesn't matter the original distribution, doesn't matter whether you're doing a stochastic control, portfolio optimization, or a medical application, machine learning. It's universal. So I'm going to present this in the form of a theorem. So again, you have the problem. Now I have added this part. The theorem says, suppose only one irreducible support set. This means that there is one support set given the solution and only one. In the convex hull example, this means that you do not have 2 points that are vertices, one on top of the other, so that one can replace the other. Then the risk is in sandwich between two functions, and therefore you can estimate the risk from the complexity very well. In the next slide, I'm going to give you a visual representation of the theorem, so details are unimportant. I would like also to add that you can also remove this assumption. That's the only assumption you can remove, and then you are left with the upper bound, which is the important part. So the risk is upper bounded by the complexity. And this is the visualization of the result. So this result says, no matter what, in the complexity risk domain, the distribution always lies in this elongated region. Not exactly. There is a thin tail that can go outside. So not sure whether you see that there are 3 nested regions in this picture. If you claim 10 to the minus 4, that is, you allow for a tail 10 to the minus 4 to go outside, then you can claim the thinnest of the elongated region. If you go to 10 to the minus 6, 10 to the minus 8, so you can really squeeze down that probability to something which for any real application is 0. 10 to the minus 10 if you want, you have just to slightly enlarge the region. So universally, for all problems in the universe, independently of the initial distribution of the data, you have that risk and complexity are linked to each other by this result. So that you measure the complexity and then you estimate the risk. This holds distribution free. You may quite rightly wonder what the impact of the initial distribution is in this story. There is an impact. So I will explain this in the next slide. So here we are back to the Orton problem. Same picture as before, I have added the elongated region, and you see very well that the distribution is within the elongated region. Then together with Simone, we run exactly the same problem with a different distribution for the generation of the data points. And this is what we obtained. The distribution is completely different. But point is that there is this universal marriage and the distribution is always in the Longuet region. Then you start generalizing. So many people say, and they are right, robust is way too conservative. I don't like. Okay, you can relax. And I'm presenting you my favorite relax scheme. So you replace this constraint with this. You say, I consider a function f less than or equal to 0. You can always do this without any loss of generality. You represent a set in terms of where a function is negative. I prefer this formulation because next I'm going to relax these constraints, and at that point f will play the role of a regret. So this is the reformulation. F, I use blue, f less than or equal to new variables, C sub I. You have as many of these variables as there are data points. C sub I is bigger than or equal to 0. When at optimum this is 0, you have satisfied the empirical constraint. If it is bigger than 0, you are in violation of the empirical constraints. But for that to happen, you pay a penalty. And rho is a tunable parameter. When rho is larger, you are basically back to robust. When rho goes down, instead you start playing a trade-off between violation of empirical constraints for the benefit of reducing your cost. I would like to mention that this setup is so much used everywhere. So let me just mention that, for example, in machine learning, if you look at the very well-known SVM, support vector machine, is exactly within this setup. Now, relax setup, and you introduce complexity. Now, complexity is the number of empirical constraints that are violated at optimum, plus the smallest amount giving you the solution. Oh, by the way, at this point, you can say, okay, I understand that your concept of complexity is different depending on the setup. Yes, true. However, if you go up to the abstract level for the scenario theory, there is only one concept of complexity. At the very abstract level, there is only one concept of complexity. When you go to the lower level, robust, relaxed, and more, then this will take different forms depending on the context. But at the abstract level, there is one concept of complexity. And exactly the same theorems as before apply. Let me now go back to this result because I believe that by now you can understand what I meant when I said, should we aim higher? Prior plus data design. So back to the portfolio optimization problem. So say that I trust that automotive gives a better reward than bank. This really means that I expect the probability distribution for the rates of return of automotive to be more up than for banking. So this is my expectation in terms of the probability distributions. I make the design, I come up with the solution, and I can measure J star, for example, whatever. I can measure empirical quantity. However, when it comes to the guarantees, this is certified whether or not the prior is correct, because my initial guess about the probability distribution for rates of return has no impact because the result is distribution free. So just repeating, You make the design, you check for features of interest, and the guarantees always remain intact. All this, in my vision, is very important for developing trust in the decision. You know that there is so much activity around on automated systems, unmanned vehicles, all that, where there is a big request for guarantees. And I believe that theories providing distribution-free guarantees can really have an impact on that. And also, you can tune hyperparameters because you can try different situations and then choose the one you prefer. So I would like to close this presentation by giving you an example about this last point. So my example, again, comes from an application using machine learning technique, SVR, support vector regression. So I will just focus on what matters. I will leave out details. So we have data points. This is two-dimensional, just to show the result, but you can think of a very complex domain. And the goal is to construct a layer for prediction. And you use this, which is SVR, exactly within the setup of relaxed optimization. Gamma is the size of the layer. This constraint less than 0 means the point must be inside the layer, but then we relax. And I'm going to show you the role of this raw parameter, the one playing the trade-off between leaving out empirical points for the purpose of improving the cost function, so having a smaller layer. In this case, we also use the Gaussian kernel, so there is a kind of, reproducing kernel, Hilbert theory, but doesn't matter. So this is the result. So I tried 15 values for rho. When rho was larger, this was the cost, the size of the layer. Then I started playing with rho. I decreased the value, and I got this value, this value, this value, this value. So I ran several times the same optimization program. And this is visible because that's the value of the program. The orange part is, again, the elongated region. So you get the full picture. And you can choose. What I chose is this value for rho corresponding to a gamma, a size of the layer 0.3, and the risk was still good enough for me. And this is the layer I constructed. Just to show you, if you go to the extreme, very large rho, so very large layer and very low risk, or the other extreme, very thin layer, but horrendous risk, you get, in one case, this one, which is, the robust solution. And in this case, it's pretty thin, and but very risky. I have last slide about the conclusions.
Thank you, Marco.
Okay, so I think that I'm well in time. So just kind of summarizing, I believe that we should aim to develop a science for data-driven optimization in the presence of uncertainty. That is, we want to optimize based on data while also providing certificates that maintain intact their validity when the hypothesized prior fails to be fully correct. What I have presented today is a scenario optimization, a body of direct data-driven methodologies with distribution-free certificates. If you allow me 30 seconds to comment on this, I would like to tell you that what I have presented today is a small portion of the whole story. So using scenario, you can do much more. You can use other risk measure, conditional value at risk, for example. And this is the important part. I have a very strong feeling that there is much, much more to be discovered. So we are really, at the first stage. I'm saying this explicitly because there are various groups in the world working on this approach, but there is really incredible opportunities for research and the community together can really advance this. I'm 100% available, to answer questions in case after the seminar, but also please reach out to me by email. I can provide you more information and directions or whatever. In any case, I believe that the results so far obtained show that the data can well stand the dual role of providing information to optimize while also accessing the quality of the user results. So I think I'll stop here.
Thank you very much, Marco, for this very interesting and stimulating talk, really. So if there are some questions and remarks, so what I can say